Hello students, welcome back. The next topic is section 3, normal subgroups. Here's the definition. A subgroup N of group G is said to be normal if its left coset and right coset are always the same. In other words, for every element G of capital G, Gn and Ng are the same. Now, if your starting group G is abelian, then this is always true. In other words, every subgroup of an abelian group is normal. So if you have to do something non-trivial, if you want to find some example that is non-trivial and interesting, then you should not be looking at abelian groups. Always you have to look at non-abelian groups if you want to do something interesting with normal subgroups. In other words, all the non-trivial examples here will be on non-abelian groups. Please brace for impact. Okay? All right, so much for advanced learning. Let's continue. Let's apply some algebraic manipulations here. You can rewrite this into that. What did you just do? Flip this G to the other side. Do you see the equivalence? If you don't, well, here's a manipulation. Multiply G inverse to both left-hand side and right-hand side from the right. And then these two cancel each other and become the identity, and we get what you want. G and G inverse is equal to N. If you don't want to do that, you can do it this way as well. Multiply G inverse, this time from the left. Consequently, G inverse G cancel each other out, become identity, and you get G inverse NG is equal to N. So this one, G inverse Ng expression, or G and G inversion, those are all equivalent. Gn and Ng. Ultimately, it all boils down to this. Now, our textbook author generally prefers this, and I'll do the same. But if I encounter some situation that this is more convenient, then I'm going to use this one too. It depends upon which one is more convenient. You got to know both. Okay, the manipulation from here to there was rather trivial, as you saw. Now let's do some non-trivial manipulation. From here, let's reduce it this way. So this equality can be reduced to this inequality. That's what I'm claiming. Wait a minute. Did I just say an equality was reduced to an inequality? You may wonder that's not usually the case. After all, back in college algebra days, or even before, which were easier, inequalities or equalities? Equalities were easier. So reducing an equality down to an inequality, that may sound a bit weird. But here we are dealing with set inclusion, so things are backward here. In this case, the equality is harder than inequality. So you see, in order to have an equality, the set A is the same as set B. That means we are including two inequalities. Set A is a subset of set B, and set A is a superset of set B. In other words, set B is a subset of set A. So in order to prove an equality, you have to prove two inequalities. But what does this theorem say? It says, no, you don't have to do both of them. Just one of them is fine. So this is actually a spectacular simplification of this. Basically, I made the problem half as difficult, twice as easy. Instead of checking 2, no, I don't need this. I just do this one. It's a big reduction, if this is true, of course. Now the question, is this true? Is it really true? Let's work it out. The proof is not that difficult, so I take it back. I just called it theorem, but it's not really a theorem level. It's a proposition. So it's not that bad. The proof is not that bad, but there's one tricky part. Here we go. Let's begin with this, except that this is an inclusion, not equality. So for arbitrary g in capital G, the left coset Gn is a subset of the right coset Ng. Then what we want is, eventually we want to have equality, so we want to prove that the other inequality also holds. Let's see. In this statement, the key is the red part. It works for every element G of capital G. So it works for all elements. So that includes G inverse in particular. So let's take G inverse. And then let's replace G inverse here. G inverse is a member of G, so that also works. And also right here, you see, we're dealing with arbitrary element. Don't we have to adjust our G like this? Arbitrary G inverse? Well, yes, we can do that, but it is not necessary. Because if I select an arbitrary G inverse, I can always go back to G and start from there, and vice versa. If I want G, I can always start from G inverse and take G inverse again to go back to G. So taking an arbitrary G versus taking an arbitrary G inverse, there's no difference. So that's the key observation. Taking arbitrary G versus taking arbitrary G inverse, no difference there. So you can just express like this. And now we can just do the algebraic manipulation. Flip this blue to the other side, and flip this green to the other side. And what we have now, previous assumption, the left coset is a subset of the right coset. Now what did we have? The right coset is a subset of the left coset. The key to this manipulation was this. Holds for arbitrary G of capital G. That was the key. Get the idea? Understanding it? Let's do it one more time. Let's do this. For arbitrary G of capital G, let's consider G and G inverse. G is blue and G inverse green for convenience. And let's suppose G and G inverse, the conjugation, is a subset of the original N. Now, this works for arbitrary G, so it works for G inverse as well, because G inverse is a member of capital G too. So let's rewrite as G inverse and G inverse inverse. Now this works for arbitrary G inverse, but oh, sorry about that, wrong place. Is it necessary to specify arbitrary G inverse? No, you don't have to, because if you want arbitrary G inverse, you can always start from G to get there, and vice versa. So taking arbitrary G inverse versus taking arbitrary G makes no difference. And then we can just go ahead with the algebraic manipulation. Flip this blue to the other side, we have this blue. Flip this green to the other side, we get this green. And what do you have? Oops, sorry about that, this green. And then what do you have? N is now a subset of G and G inverse, the conjugation. We started the assumption the conjugation G and G inverse belong to N. G and G inverse is a subset of N. And then what did he end up with? N is also a subset of G and G inverse. So they must be the same. And the key idea came from this. Arbitrary G of capital G, highlighted in red. The red part is the key. That's the hardest part. In the end, what did you get? This one here is reduced to this. Now this versus that is not that important. this reduction from here to there, that's going to be really, really useful. Okay, we got something more useful, but let's go one more step. Just one more step. This one is written in terms of set inclusion, but let's rewrite this in terms of elements. Arbitrary element of this conjugation, G and G inverse, belong to this capital N. We can rewrite like this. The arbitrary element here is G and G inverse, where G is arbitrary from G and N is arbitrary from N. So that's the key, G and G inverse. Does it belong to N? Now you can rewrite like this as well. Using the double arrow, if G belongs to capital G and N belongs to capital N, then G and G inverse belongs to capital N. Now this statement here, double arrow, versus this statement with universal quantifiers, those are equivalent, they're the same. And by now, everybody must have got used to this, but let me re-emphasize once more. What do you mean by this double arrow statement? This means this conditional statement is a tautology. It's always true. It works for all G and N. So you see, whenever you have double arrow, it includes the universal quantifier. And vice versa, whenever you have universal quantifier for all, you can re-express it in terms of the double arrow. Sometimes this double arrow is more convenient. Sometimes this universal quantifier expression is more convenient. You gotta know both. So much for the properties of normal subgroups, the definition and the properties of normal subgroups. The subgroup of G that satisfies all these conditions is called a normal subgroup. As a matter of fact, the definition involves only this one, and everything else that we did is a reduction. Reduced into this, and reduced further into this form or that form. Any subgroup of an abelian group is normal, yes. You can easily see that. And also, the kernel of homomorphism is also normal. Remember that? Back in section 2, we proved this. The left coset and right coset are the same for a kernel of a homomorphism. So the kernel is always a normal subgroup, excuse me. Let's see, we went through the definition. Now it's good time to study some examples, but I don't think we have a lot of time for that. So let's spend some time on really trivial examples, and then we're going to come back to this in the next video. Let's see, really trivial example. Oh, before that, here's a reminder. That's a definition, and then we can reduce like this, and eventually into this or that version. So this is the kind of quantity that you're interested in, which I just highlighted in bold. Let's highlight this entire thing. That's a question. The conjugation, G and G inverse, actually belongs to N or not? That's the big question. Okay. First example, the trivial subgroup is always normal. Oh, come on, that's too trivial. If you plug in E over here, what do you get? G, E, G inverse. Of course, that's just E. So yes, it goes back to this trivial group. So yes, the trivial subgroup is always normal. Next example, all subgroups of an abelian groups are normal. You can always go back to this and then use the commutativity, or you can use these. G and G inverse, change the order. G, G inverse, which disappear, and N is a member of N. Yes. We went through these trivial examples. But then again, there are some non-trivial examples, but they're going to require more time. And we don't have enough time, so let's stop here. And let's resume in the next video.